All right, welcome everyone. Thanks for showing up and learning more about ISAM. So ISAM stands for In-Space Servicing, Assembly, and Manufacturing. I am in the Space Mission Analysis branch, which is in the Systems Analysis and Concepts Directorate, or SACD. You can see here all the different people on the team who have contributed in different ways to creating this presentation and the content that goes in it. So for those of you who aren't familiar, what is ISAM? So it's this set of capabilities that lets you go and interact with spacecraft after they've already been launched. So you can do inspection, repair, upgrades, maintenance, assembly, all that type of thing. We break it into the three components: servicing, assembly, and manufacturing. So servicing is the alteration of a spacecraft after it's already been launched. So think about adding capability to something, refueling it, repairing something that's been broken. Assembly is the aggregation of components to create either a spacecraft or parts of a spacecraft. So you think of like the International Space Station. We launched it in a bunch of different pieces and assembled it all together, and now you can use it. And then manufacturing is taking raw materials either from the Earth as like feedstock or from whatever destination, so in situ resources that you collect, and turning those into usable spacecraft components. So those are the three parts. They kind of work together in this whole theme of doing something with a spacecraft after it's launched to change its functionality or extend its life or something like that. And so you can see these like nested circles. So the current capability is that like little dark blue section right there of what we can do just launching something with all the propellant that it needs, with all the capability that it needs at launch, and never touching it ever again. If you can add these capabilities, servicing, assembly, and manufacturing, then you can do so much more because you can get bigger, you can do longer, you can upgrade components over time, that kind of thing. So a brief history. So this is a chart that we developed that comes from one of our documents, the state of play, which I'll talk about in a little bit. We've been doing ISAM type things since the 90s. So the Hubble Space Telescope is a very good example of using servicing capabilities to alter a spacecraft, to improve it, to repair it, to extend its life after it's already been launched. We did that with humans. We sent the shuttle up there to grab the Hubble, and then they would replace parts or repair it. They would boost it to new orbits, that kind of thing. And so each of those missions kind of improved what Hubble could do. There's also the International Space Station is another key example. So we assembled that vehicle with shuttle and other countries' launch capabilities. We had robotics on board that were able to manipulate things. We had crew on board that were able to help assemble it. And then since then, we've been servicing it and maintaining it. So when things break or when they are obsolete, we change out those parts or we fix it. So that's another example of that capability. And you can see there's been a lot of other demonstrations that have gone on, both with the U.S. and other countries. You can see here near the bottom, OSAM-1 and OSAM-2, both of those missions have in the past year been canceled. One of those in the last week has been canceled. So there's a lot of turmoil in like what the capabilities look like going forward. But the developments that have been made in kind of preparing for those missions have really pushed forward a lot of the rendezvous and proximity operations, the robotic manipulation, refueling capabilities. So all the capabilities that we're going to talk about have been advanced in those cases. So they'll be ready to go when the next mission comes along. And feel free to stop and ask questions as we go. I'm not like I don't have like a set time or anything that I'm trying to hit. So what can we do with ISAM? So I have a few examples here. So ISAM enables persistence in space. So you can think of assets that are in space that can grow, evolve, adapt over time. You can go up there, you can expand them or replace parts that fail or upgrade them And so sometimes we call these immortal spaceships. So you basically have this spacecraft up there that you can constantly keep alive and keep relevant and everything. These types of systems can do lots of different things. They could be payload hosting platforms, so they could host science experiments, technology demonstrations. Um, uh, they could be like fuel depots or parts depots for like an eventual servicing network. So these types of spacecraft can do a lot of things, and they can grow and shrink or change over time based on what the mission needs are. ISAM enables new discoveries, so you can think of building systems larger than what you could imagine launching in a single vehicle. So think ISS. You could think of different types of capabilities that we can't do now because of the different constraints on launch or stiffness or something like that. You know, you could go up there and build these space structures and kind of tune them to whatever specific thing you need. This is an example of a 20-meter telescope that you could assemble in space, and that would give you the opportunity to kind of directly observe Earth-like planets around other stars, and those kinds of capabilities that we just don't have today. And even if you tried to do like the origami folding that James Webb did, getting to 20 meters is still pretty unrealistic. All right, and then the last thing, ISAM is the foundation for sustainable, this says lunar exploration because that's a picture of the moon, but really any human exploration. You want to be able to maintain all the systems that are on, whatever planetary body. You want to be able to protect the crew from things like radiation or micrometeoroids. You want to be able to kind of make these things bigger and more capable so that crew can stay for longer durations and do more science and exploration and that type of thing. In order to do that, you need a lot of infrastructure in place, power, communications, life support systems, propellant in order to move things on and off the surface, that kind of stuff. And ISAM is really kind of the key to making all that work, the robotic manipulation and assembly and construction of the different things. If you have propellant being produced on the surface, you need all of your vehicles and your landers and stuff like that to be able to accept that propellant. So they need that refueling capability in the system itself that you're going to use. So again, ISAM is kind of this foundational capability that's needed for sustainable exploration. Okay. All right, so now we know what ISAM is. Who are we as the ISAM working group that is over in SAC-D? So we help the agency and really national leaders, so other government agencies as well, understand the past, present, and future of ISAM in the space ecosystem. So, what have we done before? What could we do in the future? And how do we kind of get from where we are to there? So we have 5 different swim lanes that we maintain in doing all this. The first is the ISAM State of Play, which I'll talk about in more depth here in just a second. This is an annual document that captures the current state of ISAM technologies, developers, facilities, all that type of stuff. Second is systems analysis. So tools and methods to analyze these ISAM-enabled capabilities. So a lot of the tools that we use are based off of previous spacecraft or designs or concepts. And when you start talking about assembly and servicing and all that stuff, you kind of get away from that heritage and you have to think about completely new ways of doing not just the sizing, but also the cost and how do you do contracts and all that type of stuff. So we're working on that. And I'll show an example of what we've done there. The ISAM ecosystem. So this is a collection of the different ISAM related concepts that have been developed from government, industry, and academia, all in one place so that we can kind of, if you want to know ideas for building large telescopes or large observatories, we can kind of talk about all the different ways that people have thought of doing that. If you want to talk about surface exploration and infrastructure, we can look at all the different ideas for that as well. The next is gap analysis, helping agency leaders generate, visualize, and analyze ISAM capability gaps. So many of you know that STMD maintains a set of gaps in what capabilities we don't have to do the missions that we want to do in both human exploration and science. And the system capability lead for ISAM and RPOC, we support him in developing and maintaining that set of gaps and kind of understanding where all that plays with all the different capabilities that we've been developing in the state of play, and then where we want to go in the ISAM ecosystem. And then the last is the strategic support. So agency and national ISAM activities, advocacy, outreach, all that type of stuff. We support several different organizations, and I'll kind of go through the timeline of all of that kind of near the end. But just how we've supported all the different ISAM activities that go on across the government. And there you can see the pictures of the teams. So we have several of them in the crowd. So if you see any of them and have ISAM related questions, feel free to accost them with your questions. All right, so let's jump into the ISAM state of play. So what is this? This is a document that characterizes the current state of ISAM capabilities. So we have this compilation, this giant document that has all these past, present, and then some of the near future things that people are working on in ISAM. And our intent was that this could be used in any number of different ways. We wanted to make a reference document that was kind of easy to use for whatever purpose you may have. So mission designers, if they're making new concepts and they want to see what kind of ISAM capabilities are out there that they could leverage, this document does that. If they want to create roadmaps or technology development plans, they could look here and see what's been done, kind of what that left-hand side of the roadmap might be, and then what's going on right now, so you understand, what people are developing and you're not trying to duplicate, or you can maybe build off of that. And then the last thing is helping people who are in these specific technology fields, being able to see kind of what's going on in the rest of the ISAM world that is, kind of adjacent and relevant to them, so that they're not kind of in their little bubble, and they can kind of see what's going on everywhere. And this is updated annually. That may change if we get to the point where we're not making a lot of changes every year, then we may slow down. But even now, we're still like 20% of the document is new every year. New things are happening a lot. We're finding out about things that have happened that we didn't know before. We come up with things that we want to add because someone starts asking. So I'll get to a couple examples of things that we've added over the years. But yeah, the document is living, and so we're constantly seeking out information from industry and academia and other government agencies and other people within NASA to help us kind of figure out what we're missing, what we can improve, what's changed, that kind of stuff. And that fits within this overall capability assessment process. So I think of this as a cycle. So we start out with where are we now? So that's the blue ISAM state of play that characterizes where we are. Then the ISAM ecosystem is kind of the vision of where we want to be in the future. We want to have these sustainable lunar outposts or infrastructure. We want to have these large telescopes. We want to have these immortal spaceships. And so that kind of gives us the vision of where we want to go. And then the orange part is how do we get there? So understanding what those concepts need, what are the gaps, how do we invest in those and actually close those gaps? And then that feeds back into the state of play that says, where are we now? Now we're, at some better point than we were at the previous iteration. So that's kind of how this all fits together. So here's an overview of what the state of play looks like. This is the 2023 edition. There are cards on that table by the door. If you want to grab them, they have a QR code that'll take you right to the site. You can go download the document and take a look at it. We start out with the history of ISAM, so that's that timeline that I showed at the beginning and kind of what's been done before. We have 11 different ISAM capability areas. So these are the different functions that you would perform in an ISAM mission. And I'll go over those in a little more detail in just a second. And then like, what is the state of each of those capabilities? So we have some description of kind of where we are in the world in that area. And then we have lots of information that goes into our appendix that kind of details each specific technology that we found. This year we have ISAM developers and facilities. This is a new piece of the document. So the developers, each of those technologies has been developed by someone, and so now we have profiles on each of those developers, and you can see for each one, kind of across all the different technologies in the document, what they've worked on. And then facilities, both on Earth and at ISS, what different facilities are there to test and demonstrate ISAM capabilities? We have key ISAM missions. So a lot of these technologies are a part of a larger mission. So a mission will do, rendezvous and capture, then it'll do some robotic manipulation, it'll refuel, it'll do some assembly, so all of these different, capability areas that you'll see in a minute, are done by a single mission. And we wanted to keep all of those together so that you can say, oh, what is ISAM 1 supposed to be doing in space? And then you can kind of see across all the different capability areas what they're doing. And then lastly, the appendix has all of the information from our repository in the Word document so that you can kind of read the description, who's doing it, what country, some of the specific performance parameters. So, how many degrees of freedom for a robot arm, or what's the reach, or what the material that is being recycled, or something like that. So all that information would be in the appendix. So you could go and dive deeper into each specific technology. And we release this every year. We kind of frame it as being a crowdsourced document. So we're constantly asking for feedback from people to help us make the document better. We kind of recognize that we're not going to get everything the very first time through, so or even the third time through. So we ask everyone to give us their input, and we release it annually, and then we present it at different conferences and different like ISAM community activities, requesting folks to let us know what we're missing, or if they're a small company, what they've been doing over the past year, so we make sure we're up to date. And so we collect all of that, and then we put that into the cycle for the next year. So every year we're constantly seeking feedback, incorporating it, seeking the feedback on that, and then incorporating it. All right, so here are 11 different capability areas. Grab my water here. So we see these as functional areas. So these are the types of functions that a spacecraft would do using ISAM capabilities. These wouldn't necessarily be like distinct missions by themselves, but you could think of a mission that would do any number of these functions. And we wanted to characterize what the state of the art of each of those are. So we've got robotic manipulation, so different robot arms and what they're doing. Rendezvous proximity operations, or RPO, capture, docking, and mating. So this is approaching another spacecraft, grabbing it, docking to it. This is where things like fiducial markers come into play, and grapple fixtures, all that stuff is part of that. Relocation, so boosting or just moving another spacecraft, taking over its propulsion capability and moving it somewhere else. There's a commercial example of this called the MEV, Mission Extension Vehicle, that Northrop Grumman operates. And they basically have another spacecraft that goes and grabs on to a geo communication satellite and takes over its propulsion, and therefore extending its life. So that geo spacecraft doesn't have to worry about running out of propellant, because it's got another spacecraft now that took over that capability, and so it can continue operating and making money for the company over time. So they have 2 of those spacecraft up there that are operational, and that's an example of that relocation capability area. Then the next 2 are kind of similar, but have one important distinction. There's planned repair, upgrade, maintenance, and installation, and unplanned or legacy repair and maintenance. So the legacy, or the unplanned servicing, is a spacecraft that was designed, built, and launched without the intent of ever touching it again. Like no one no one expected anything to come and refuel it or upgrade it or change it or anything. And so there's a lot of different capabilities that you need to add to your servicing spacecraft to be able to, rendezvous and capture with something that was never intended to be rendezvous and captured with. Cut away MLI and switch out the fill and drain valves with a cooperative one so that you can refuel it. All that type of stuff you have to do if your client spacecraft was never intended to be serviced. The other end of that is the planned servicing. And so in that case, your spacecraft, as you're developing it, you're expecting something, a servicer of some sort, to come and refuel it, swap out parts, add more power, that kind of stuff. And so you'll build in modular interfaces, you'll build in the fiducials and the grapple fixtures so that that servicing spacecraft can easily grab a hold of it. Refueling and fluid transfer, that's fairly straightforward, just transferring of propellant or some other fluid. It could be like pressurant or something like that. Life support fluids, those types of things. You can transfer it from one system to another. Structural manufacturing and assembly. So this is building structures, big trusses or towers or beams or anything like that that you could then use. Recycling, reuse, repurposing. So taking either a full spacecraft or subcomponents or the raw materials and repurposing those into something else. So if you have a lander that lands on the moon and that's all it does and it sits there forever, could you take those tanks and turn them into something else? Could you melt them down, turn them into structure? Could you just take the tanks and use them for tanks as, for some other use? So all of those kinds of things fit into that capability area. Parts and goods manufacturing. So a lot of you have perhaps seen the 3D printing stuff that they've done on ISS. That's where this comes into play. Making tools, making spare parts, all that stuff fits in here. This year, we're going to start adding in creating or manufacturing materials for use back on Earth. So fiber and proteins and stuff like that is going to go in that parts and goods manufacturing section. Surface construction. This is building things on the surface, landing pads, berms, towers, shelters, all that type of stuff that you would build on the surface. Use all the same capabilities for, ISAM. You're manipulating things, you're building things just on the surface. So slightly different application. And then finally, inspection metrology. So this is if you have a spacecraft that fails to deploy something, the ability to go and inspect and figure out what happened. If you're assembling something or building something that's really large, you want to be able to do the metrology and measure as you're building it to make sure that you're making it straight or curved at the appropriate curvature that you want and that kind of stuff. So these are the 11 different capability areas that we decompose the document into. These are the types of technologies that we're tracking, that we're keeping aware of for all the ISAM world. And this year we have 220 of these different technologies, and you can kind of see how they fit in those different capability areas. So a lot of the more mature ones, robotic manipulation and RPO, we've done that a lot in the past. So there's a lot of information there. Some of the stuff that we haven't done a lot of, legacy repair and maintenance, recycling, reuse, repurpose, those are less mature. And so there's a lot fewer entries in the technology repository that we have. But the idea is all of this information is in the repository so we can slice it and dice it and look at it in different ways, however we want. Some just examples of the types of stuff that's in the state of play. So each section we tried to include some figure that was meaningful, and so each section kind of has a different flavor. Some of it's more categorical, so we're kind of characterizing the types of things that have gone on, and so you can see there the Venn diagram and then that table at the bottom for surface construction. Some of them is kind of temporal, so we have the refueling and fluid transfer, so you can see over time what types of refueling demonstrations and kind of operational capabilities have been out there. And then finally, robotic manipulation over on the right. We've got that sorted by arm length or reach, as we call it. And then we show like which ones have been flown, which ones are in development. So you can kind of see, which robot arms are available to us. And every year we find new robot arms that are out there that people are either working on or flying. So there's still a lot going on in the robotic world. All right, and then the last kind of content thing for the State of Play are all the developers and facilities that we added this year. So we have 88 different ISAM developers. And again, each of those are tied to one of those technologies, those 220 technologies in the document. So you can see for a given developer what different technologies they've been working on. And then we also have 50 different ISAM facilities that we identified, and you can see kind of the high level where those facilities are. A lot around the coast, not a lot in the middle of the country, as a lot of areas are in the in the United States. So yeah, we also have ISS there, so you can't forget that ISS is also a demonstration facility, and so we have several different things on ISS where we can host payloads or we can do different demonstrations inside the pressurized volume and everything. So all of those are captured as well. All right. All right, just a quick kind of evolution of what the State of Play was. So the first one we released in 2021. And so we just finished up our third. We're on our fourth iteration for this year. And you can see each year we kind of are adding significant content to the document as things happen, as we learn about stuff. And again, we're constantly seeking feedback from folks who are actually working on these technologies to help us. And we have some handouts. They're over on the table by the door if you want to grab them. So it's got our QR code so you can go download the document. It's also got our email distribution on there so that if anyone has something they want to add to the document, they can reach out to us and that'll send the email to the whole team. And then we'll put it on our list to look at for the next iteration. All right, links to download it. And there's our email again. Any questions on State of Play before I completely switch gears? Okay. There'll be time at the end, hopefully. The next, I want to talk about the space superhighway. So this is a concept for space infrastructure that we developed as part of an interagency team. So we were working with Space Force, AFRL, the Aerospace Corporation, and we were trying to come up with an idea for what space infrastructure might look like that would benefit all of our different government use cases that we may have. And so we came up with this space superhighway concept. And this was presented at the IAC in 2022 in Paris. And it has been well received. I think the Space Force is a little more gung-ho about actually implementing this. They're taking a lot of measures on setting up kind of their logistics network and refueling of their assets. So they're taking a very proactive approach to making something like the space superhighway a reality. And so what started all this was we had all these different things that we wanted to have happen in space. So like imagine a future where we could protect the cislunar activity in commerce. So that's like Space Force's #1 priority. Define norms of behavior so we know what is not allowed. So if some other country comes up to our spacecraft and stands in front of it or something like that, we'll know that that's not allowed, or that's like an aggressive action or something like that. So things like that. Sustainability, provide logistics, utilize technologies, create a space economy, all these types of things we want to do in space, and sustainable space infrastructure can really support that. And that space infrastructure heavily relies on all those capabilities that I just talked about that ISAM can provide. So we looked kind of backwards to show some historical examples of infrastructure that have kind of helped our country, and kind of the three different columns there you see are kind of the three different key pieces of infrastructure that are present. There's the transportation part of being able to move from point A to point B. refueling and services, so having the sustainable and maintainable infrastructure and then the ability to kind of move around. And then finally, the economic growth that comes with being able to connect, producers and consumers and that kind of thing. So we looked at the transcontinental railroad of the 19th century, the interstate highway of the 20th century, and so for the 21st century, we need a space superhighway as our transportation infrastructure goal. And so that's where we came up with the space superhighway name. And so this is what it looks like. We have, well, notionally what it looks like. It's not to scale, not a real drawing. It consists of 3 different pieces. Regional hubs. So these are like your footholds in space. This is where your servicing vehicles can be based out of. This can provide utilities to different hosted payloads, Earth observation or technology demonstration type stuff. It can provide like refueling services and that kind of stuff to spacecraft. So this is like really the service stations, the hubs that all of your transportation network kind of builds off of. And these are located in different orbits. And each hub is kind of unique based on what the demands are in that region. And so it's kind of very flexible what you would actually have this be. The next piece is a sustainable transportation network. And so this is being able to move between hubs. So, if you have materials and raw materials or propellant or something like that you want out in cislunar space, maybe it can go through this transportation network and it can all get launched to like a LEO hub. And then you can have a tug that aggregates or that collects that aggregated propellant and then ships it out to cislunar space and then comes back to either return stuff from the moon or, comes back to pick up another load that goes out to the moon. So you can imagine this like a network of tugs and servicers and all these types of vehicles that are, transporting in between these different hubs and then from the hubs to, points of interest. So you have maybe you have a geo hub that has lots of propellant on it, and then you have a servicer that goes out to geo satellites and refuels them, or it has lots of spare parts or propulsion modules or something like that, and it takes it from the hub and takes it out to those geo spacecraft. So that transportation network kind of builds off of all those hubs and can kind of move things around. And then the last piece is Earth to orbit logistics. So if you have kind of this vibrant cislunar space economy and there's lots of stuff going on, then all that has to be launched from Earth at the beginning. And then if you have these kind of standardized destinations, standardized interfaces and packaging and stuff like that, it can really help kind of with that Earth to orbit segment of the transportation infrastructure. All right, and then
since you're talking about economy, if you look at the scale of this, do you have a sense of how big it is? Like I was wondering, for example, when we first built the interstate system, and what the total cost was back then relative to the total, say, GDP of the U.S., and what would that be for this?
That's a question I don't have an answer to, but the scale of the space superhighway, you could start off small with like a single hub, say clustered around a like a LEO constellation or something in GEO that is maybe centered over the U.S. that the U.S. could use to service its satellites. So that's kind of like our first step that we envisioned was something kind of small and local, and then as capabilities grow, maybe the gateway is part of this network, and so then you have some logistics. Transportation between LEO and the gateway that kind of goes back and forth. So I envision it as something that evolves as the need arises. And so I don't, that's a good question about percent of the GDP and all that kind of stuff. I don't have an answer for that.
So we're still thinking Lewis and Clark, not state.
Yeah. Yeah, if we had like cities on the moon and stuff, then maybe that would be a different story. But all right, another thing that we talked about in this interagency group were what are all our different use cases for this transportation infrastructure. And so we, put a lot of them on this slide, kind of highlighted a few of them that maybe warrant some further study. The first is a persistent asset that can host payloads, that can hold logistics and propellant and things like that for use elsewhere. Demonstrate technologies. So if any of y'all are familiar with the Ramses concept that was developed here at Langley for several years, that's an example of something like this. It's a persistent asset that can host payloads and different commodities that might be used in space. Deep space servicing capability that could, maybe service different spacecraft like Gateway or deep space telescopes, things like that. What are the different types of servicing vehicles that we could envision that would use some sort of transportation infrastructure like this. And then the last one, active debris remediation. So there are concepts for debris disposal, end of life removal, that type of thing. And you could either have a dedicated spacecraft that goes up and disposes of 4, 5, 6 things, and then it's done, or it could use this infrastructure that exists and refuel and kind of continually remove things. There's also lots of different concepts for small debris removal that aren't a dedicated spacecraft that goes and grabs things and deorbits them. And so those things like space lasers, stuff like that, you may need lots of power in space. And so you could generate those powers with these persistent assets potentially. All right. So this is all like the early kind of concept formulation for what the space infrastructure could look like. We're kind of actively going and trying to do some analysis on, where does this make sense versus dedicated spacecraft, which locations would make sense for hubs, how big those might be. So, we're doing a lot of that analysis, and people like the Space Force are also interested in understanding, like where those break evens are and stuff like that. So there's a lot to be done here. Yeah.
Okay, piggybacking on that, have you looked for a need for this? Because I don't know, most SACD studies to me have taught me that my intuition on what sounds like a good idea isn't necessarily a good idea. You have to do the logistics behind it and understand the use cases and understand what it takes to get a pound of propellant from one place to the other, and so on. So you have to balance that again, of course, against what's just a new one cost. And then is there a business case at a minimum, or at least not a bankrupt a country case, in order to kind of let some of this become real? Is that something that's kind of part of that study, to make sure not just, understand what a small constellation of it would cost, but that, there's an actual need, as opposed to just building 3 extra copies of everything ever, and it would still cost less than maybe this whole super.
That's the exact type of analysis that we're doing. We're trying to understand where that breaks even. If you're trying to refuel one geosatellite, probably doesn't make sense to have infrastructure that supports refueling that one geosatellite. If you're trying to refuel hundreds, then maybe it does make sense to have some infrastructure in place that your servicer can go back and refuel and all that thing.
And even just like the thing has to keep working too, right? Like,
Just
your electronics have to keep working and your transmitter has to keep transmitting.
So there, there's definitely a break even, and we don't know exactly what that is, because it's going to be different in every situation. And in a lot of situations, it doesn't make sense in and of itself to use the infrastructure, right? Like, it doesn't make sense to have infrastructure in place just to do debris removal, right? But if you have infrastructure in place for 10 different use cases, then leveraging that infrastructure does save you. So it's like not an isolated problem of like, does this business case make sense? Does this business case make sense? It's like, how many business cases do I need to collect in order for the aggregate to make sense? So it's not a simple problem. So we haven't solved it yet. But that is like kind of the key for that whole systems analysis product line, is kind of being able to quantify the benefit, the cost, the risk, all that kind of stuff. of these types of architectures. So you asked the right question. We don't have the answer yet. Okay, so we also have handouts on Space Superhighway over there on the table. This will take you to the website that has a lot of the different published works that we have released on Space Superhighway and the different studies that we've done. So check that out if you are interested, and it will be updated regularly as new things get published. All right, the last topic that I want to talk about is our strategic support. So this started in 2016 or so with the Space Science and Technology Partnership Forum, or S&T Partnership Forum. And that is a kind of a partnership with NASA, NRO, at the time it was Air Force, now Space Force, to look at technologies or capabilities that are potentially of interest to all three agencies that we could maybe collaborate on and make sure we're not duplicating effort, or we can build off of what others are doing, because we don't always talk to each other. Especially if you're the NRO, then you don't talk to people. So that was a forum to get together, and then the 2016-2017 topic was in-space assembly. And so the team in SACD did the data analysis and facilitation. So we went to all the different agencies to understand what they wanted out of in-space assembly, what capabilities they were working on, and then kind of brought it all together to understand how we could maybe work together and collaborate. And we have several papers that we published in that time frame that kind of talks about how we did that. It doesn't always have all the data. There's like an internal government report that has the data on kind of where we want to collaborate. But what came out of that was, yeah, there's a lot of interest here from all three agencies, and we should really keep talking about this and keep coordinating what we're doing and all that type of stuff, and not just kind of let this go away. So after that was the ISAM National Initiative, which was kind of a grassroots, coalition of the willing type thing, where we got together routinely with the other government agencies, and a lot of the stuff that I've talked about thus far has come out of that national initiative. I was the chief architect for that at the time, so I worked with the other agencies' architects to kind of figure out what our common interests were and all that. So that's what started the state of play, and the Space Superhighway came out of it and everything. That got noticed by the White House and OSTP, and so they created this ISAM Interagency Working Group in 2022, and that was kind of like the formal, all the agencies get together and talk about what our national strategy is and what we want to actually do. So 2 documents were produced that year. The ISAM National Strategy, which you can see over there on the right, had those 6 different strategic goals, and those are varied from like the technical stuff, like advancing the research and development and the infrastructure, all the way to kind of like the workforce stuff and like making sure that we're not being outcompeted by China and that kind of thing. So there's those 6 strategic goals, and within that, there's the ISAM implementation plan, which has actions for all the different agencies that, hey, go do this to support this goal. And so that's what we've been working under for the last couple of years. And one of those implementation plan activities was to create a national consortium for ISAM, and that includes government, industry, and academia. And that is called COSMIC, Consortium for Space Mobility and ISAM Capabilities, which as of this week, NASA is officially a member of the consortium that we've been paying for like a year and a half. So yay, lawyers. So we're going to have an active role in COSMIC and what that becomes, and I'll talk about that more here in just a second. I wanted to kind of highlight, here's a slide that we created on the ISAM implementation plan. And so you can see those 6 different strategic goals, and then each of the implementation actions underneath it. The ones with the blue meatball are things that NASA is the lead on. and the ones with the gray meatball are the things that NASA is supporting on. So you can see NASA has a pretty big role in all the implementation actions. And then I've highlighted 3 of those in yellow. The first one is define, estimate the value, and prioritize future missions and architectures that will be enhanced by ISAM. So I showed you the space superhighway. I talked about the ISAM ecosystem as that collection of different concepts. So we're kind of an active role in that number. And then the other one, maintain a repository of available ISAM capabilities, facilities, and gaps. So we were able to get the state of play in there. So, we had been working on the state of play for a couple years at that point, but it's, one of our implementation actions, so we can, easily check that box. And then the third one that I've highlighted over there is establish the National ISAM Consortium. And so that is COSMIC. That's being run out of STMD. Go to the next slide. And so STMD established COSMIC. For those of you who are familiar with like LSIC, which is the Lunar Surface Innovation Consortium, that's also being run out of STMD. This is kind of a similar situation where NASA is paying a consortium management entity, which in this case is the Aerospace Corporation, to run the consortium and take notes and set up the meetings and all that kind of stuff. There's a steering committee that is government, industry, and academia representatives. There's 12 people on there. 2 of them are from NASA, Bo Nas, who's the system capability lead for ISAM, and Carolyn Mercer, who's the chief technologist for SMD, Science Mission Directorate. So the 2 of them are on the steering committee that help define what the consortium is doing, what actions there are, make sure that they're kind of in line with the interests of the community, being government, industry, and academia. There are 3 caucuses, government, industry, and academia caucus. And so that's like a forum for each of those different organizations to kind of get together and talk about things that are of specific interest to them. So at the government caucus meeting, at the kickoff, we all got together and we talked about what we needed, and some of the stuff we wouldn't want to talk about in the industry with the industry folks there, contracts and things getting canceled and stuff like that. We were able to talk about that in the government caucus, and like Space Force and NASA had like good back and forth on what they were interested in and how they could help each other, that type of thing. And I don't know what happened in the industry or academia caucus, so I wasn't there. And then there are 5 different focus areas, and you can see the different focus areas there. Each of those cover different topics. So research and technology is, what are the up and coming technologies that are being developed, and how can we help create roadmaps, get them infused, all that type of stuff. Demonstration infrastructure, this is ground, space, and digital infrastructure. So like ModSim fits in there. How do we develop these modeling frameworks to be able to test digitally how you assemble a 20-meter telescope, that kind of thing. Missions and ecosystems, what are the concepts that are out there? What does the space superhighway actually look like when you take into account what industry wants, what government wants, and academia? Policy and regulation, all the different things that you need to worry about when you go and mess with a spacecraft that's already been launched, fit in there. Getting all the permissions and certifications and stuff like that to operate all fits in there. And then finally, workforce development. There's not an ISAM degree. So, like the workforce isn't necessarily being, specialized towards ISAM, but there's a lot of different capabilities, robotics, autonomy, structures, all this type of stuff that are kind of in the ISAM field. How can we foster those, that new workforce coming along? All right, so that's the end. That's all I got. I just want to kind of like finish off here that, again, like ISAM capabilities are the foundation for the sustainable exploration and operation. So, being able to maintain things, reuse things, repurpose things, build really large structures, all of that stuff relies on these ISAM capabilities and the development that they're doing. And, if we really want to be a spacefaring civilization and kind of go out and live on all the planets and the moons, then these are capabilities that we like can't get by without. Like, you can't expect to just launch something and then never touch it again, have it last for 20 years with people living on it and banging on it and stuff. So